Alright guys, Mr. Carlson here. Today we're going to talk about electron configurations. When we're talking about electron configurations, it's basically just where electrons are held within an atom. So for this first part here, electrons are within, are within orbitals, and orbitals are within what are called sublevels, and then the sublevels fit within the energy levels. So energy level being the biggest part, and then within that sublevels, and then within each of the sublevels there are the orbitals. If we look at, not that diagram, but this diagram here, so this is what we would call a Bohr model. In the middle here, this is the nucleus. This is where we've got the protons and neutrons, and then as we move out from there we've got these specific distances away from the nucleus, and this is where the electrons are held. If you look here, we've got S, and then in the second energy level we've got S and P, and then we keep going up from there, S, P, D, and then in the fourth energy level, S, P, D, and F. So the further we get away, the higher the energy level and the more sublevels that we can fit. Now remember, within each sublevel, there's a specific amount of orbitals that can fit in there. S is the smallest one. You can fit one orbital. P would be the next up from that, where you can fit 3 orbitals, and then D can fit 1, 2, 3, 4, 5, and then the F sublevel can only fit, or sorry, not only, but 7 would be the most. 1, 2, 3, 4, 5, 6, 7. And then within each orbital, we can fit 2 electrons. So I'm going to show electrons using these arrows like this. So I can fit 2 electrons in each orbital like this. And so that's the pattern that we're going to see with these energy levels. So if we come back over here, for the S sublevel, I can only have 1 orbital. For the P sublevel, I can have 3. D, I can have 5, and then F, I can have 7. And then each orbital, doesn't matter which sublevel it's in or at which energy level it is, it can only hold 2 electrons. So if we look at the first energy level, which has only the S sublevel, we would write it like this, 1S, and then we could put a line here. Sometimes it's drawn like this with a box, and sometimes with just a line like this. It doesn't really matter, it's showing the same thing. And how many electrons can fit in that shell, or that energy level, the first energy level? Well, it can only be 2, because I can only hold that S orbital, and it can only have 2 electrons. If I go up to the second energy level, so now I've got S and P, so the way I would write it is like this. I'd write 1S with a line, and then I would go, or sorry, not 1S, I would go 2S since it's the second energy level, so 2S with a line, and then 2P, and then remember the P sublevel can have 3, so 1, 2, 3 orbitals, and then 2 electrons at each. 1, 2, 1, 2, 1, 2. So the total amount of electrons that I can fit at the second energy level, 2, 4, 6, 8, would be 8 electrons. 2 electrons on this one, I forgot to write that down. Then if I go up to the third energy level, so now I can fit S, P, and D sublevels. So if I were to write that out, that's like 3S with its 1 orbital, 3P with its 1, 2, 3 orbitals, and then 3D, and then remember D sublevels can hold 5, so 1, 2, 3, 4, 5. And then again, I'm not going to draw in all the arrows for this, but we could just count up. So there'd be 2 electrons here, 4, 6, 8, 10, 12, 14, 16, 18. I could fit 18 electrons total at the third energy level. And then for the fourth through the 7th energy level, so all of those energy levels can hold all 4 of these sublevels. We're not going to need more than the F, not more than these 4 sublevels at each of these energy levels. So let's just look at the fourth one for an example. So it would be like 4s with 1 orbital, 4p with 1, 2, 3, 4d with 1, 2, 3, 4, 5, and then 4f with 1, 2, 3, 4, 5, 6, 7. And so again, 2 electrons in each of those orbitals that I can fit. So if I were to add up how many electrons I can fit, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32 total electrons that I could fit at the fourth energy level. So if we come back to this, the further we go out with each successive energy level, the more and more electrons that I can hold at each one. Now, when we're actually making the electron configurations, there's a couple of rules that we need to follow when we do that. The first one is called the Pauli exclusion principle. So this one says that electrons in the same orbital must have opposite spins. So if we look at nitrogen's electron configuration, for example, nitrogen has, I'll write this over here, has 7 electrons total. And so when we write the electron configuration, we're trying to show where do all those electrons fit, or basically at what energy levels and within what sublevels are those 7 electrons. So we're going to start 1s and 2 electrons there. Then I would have to go up to the second energy level, so 2s, and I can only fit 2 electrons in there. So right now I'm showing 4 electrons. I want to show a total of 7, so I'd have to go to 2p, because remember at the second energy level I can have s and I can have the p sublevels. So now I can fit 1, 2, 3 orbitals within that one. So I'm at 4. I want to get to 7, so I'm going to have to put 3 in there. So 1, 2, and 3. And notice that I spread these out into individual orbitals first before I pair them up. We're going to get to that in a second. But the main thing is, this is what the orbital diagram would look like for nitrogen. So an orbital diagram is showing each individual orbital, and it's using these arrows to show the electrons in each one. By the way, sometimes you might see these arrows drawn like this, where it's kind of like a half an arrow, but sometimes they might be drawn like this with a full arrow. It doesn't matter, they're both saying the same thing. I think most of the time you're probably going to see it like this with this half arrow, but again, either way, the main thing you want to show is that they have opposite spins. So within this, one arrow has to be pointing up and one arrow has to be pointing down. You can't have 2 arrows both pointing in the same direction. One has to be positive and one has to be negative. So that's the first rule. The second one, which is called the Aufbau principle, this one says that electrons will occupy the lowest energy level possible before they start occupying the higher energy levels. All this means is that when you're making these electron configurations, you start with the lowest one first, and you just keep building it up from there. So if we come over to this screen right here, that's what this is showing, is that you can't just start putting electrons. So let's say we were making the electron configuration for aluminum, for example, and we started to put electrons into its electron configuration. I can't just start anywhere within this. I can't just start at, let's say, the 2p level and start filling electrons there. I have to start at the lowest one, and I have to build it up from there. Now the tricky thing is once you start getting higher and higher, the electron configurations become more and more complicated. So for example, if you look here, we start at 1s in the first energy level, and then the next highest energy level is 2s, and then 2p, and then after that 3s, and then 3p. But notice what happens right here is actually, instead of going right from 3p right to 3d, this one, notice, is put right in between. The energy is actually in between these. That's because the 4s sublevel is actually lower in energy than the 3d one. So what would happen is, as we're putting electrons in here, after we fill up the 3p orbitals, we would have to fill up the 4s orbitals first, then start filling up the 3d, then start filling up the 4p, and keep going from there. And it actually starts to get even more complicated when we get up to the 5th energy level and the 6th energy level. But there's a trick in knowing the order of that, and we'll see in a little bit here how we can use the periodic table to help us figure out the order in which we fill up those energy levels. So let's come back to this screen here. So that's what the Aufbau principle states, is that you have to fill up the lowest energy levels first before you start going to the higher ones. And then the last one is something called Hund's rule. This means that electrons will spread out into different orbitals before they start pairing up. And this right here is what we're talking about, what I did earlier with nitrogens. So let's do oxygen for an example. If I'm going to write out the orbital diagram for oxygen, oxygen has 8 electrons total. And it's just got one more than nitrogen. So we're going to go 1s, and it's got 2 electrons there, then 2s with 2 electrons, and then for the 2p orbitals, so watch how I write this. It's going to go, we're going to go 1 here, then 1 here, and then 1 here, and then we'll start pairing up these other ones. So right now I've got 2, 4, 6, 7, and so now I can pair it up like this, and now I've got all 8 electrons. If you were to write it like this, let's say, you put, so there's 4 electrons right here. Let's say you put it like this instead. This would be incorrect because you've got an open orbital right here, and these electrons are going to want to spread out from each other because they're all negatively charged, and so they kind of repel each other, and so they want to spread out as much as possible before they have to share an orbital. So this one would be correct, and this one right here would be incorrect. All right, so that's called Hund's rule. So now let's get a little practice actually writing out some of these electron configurations. Let's come over to right here. So if you look at this, this is a blank periodic table, and it's broken up into different sections. So we can break it up into the S block, which is right here. We can break it up into the P block, which are these elements over here. And then we've got the D block in the middle, where the transition metals are. And then the F block, which contains the lanthanides and the actinides. Remember that this block here, these lanthanides and actinides, this fits in this section right here. So we want to remember that the periodic table actually should be much wider. So this should kind of break in the middle, and this F block should actually fit in between here, between the 6s and the 5d. So just keep that in mind when we're writing out these electron configurations. Let's say we have to write the electron configuration for sulfur. Here's how we're going to do this. We're going to start up in the very top corner right here where it says 1s, and we're just going to count how many electrons it takes to get from the beginning here all the way to the element that we're interested in. So sulfur would be right here on the periodic table. And so what we're going to do is we're going to count starting right here, and we're going to count our way to sulfur, and then we're going to write out the electron configuration as we go. So starting right here, we're starting at the first energy level, 1s, and this sublevel would be full, right? So we would just put how many electrons that it would take. So we would count 1, 2. So 1s, 2. There's 2 electrons at that 1s orbital. And we'd keep going from there. So now we'd come down to this spot right here, 2s. So we put 2s, and then we put a little 2 right there, because this orbital would be full because I still haven't reached sulfur yet. So 2s1, 2. And then I'd come over here, and now I'm at the 2p sublevel. So then I'd count 1, 2, 3, 4, 5, 6. That one would be full as well. So 2p6. I'd write it like that. Then I jump down here, 3s. So I'd write 3s. I'd count that, 1, 2. Put that there. Then I'd jump over to this spot, and now I'm at where sulfur is. So now I'm going to go 3p and then count how many it takes to get to that spot. So 1, 2, 3, 4. And so that would go here, meaning I've got 4 electrons in that 3p sublevel. And that would be the electron configuration for sulfur. Let's try another one. Let's try, we'll try neon. Let me erase this real quick, give some room. So neon. Neon would be right here on the periodic table. If I were to write that, we again count it up. So 1s2, 2s2, and then 2p, 1, 2, 3, 4, 5, 6. 2p, 6. Now, actually I shouldn't have erased sulfur. Let's bring sulfur back real quick. Let's rewrite that real quick. So 1s2, 2s2, 2p6, 3s2, 3p4. If we look at this, notice that the first part of neon's electron configuration here, 1s2, 2s2, and 2p6, it's the same as the first part of sulfur's, right? Which makes sense because for any of these elements on here, we're going to kind of keep repeating that pattern if we're always starting up here in the corner. The first part of that electron configuration is always going to be like 1s2, 2s2, and it's going to keep being the same pattern. So instead of writing out the entire pattern over and over again for each element on here, what we can do is we can use what's called a noble gas configuration. So for example, for sulfur, since this first part right here, 1s2, 2s2, and 2p6 is the same as neon's, what we can instead write is this. We can put the symbol for neon in brackets, and then we can put 3s2 and then 3p4, like that. And what we're essentially saying is, by us putting neon in brackets, what we're doing is we're saying, okay, we're saying neon's electron configuration right here, so that 1s2, 2s2, 2p6 would go here, and then we pick it up after that for 3s2, 3p4. So if we look at on the periodic table, here's neon, right? So what we're saying is we're gonna say neon's electron configuration, and then we pick it up from neon, so it would go 3s2 and then 3p1, 2, 3, 4. Let's try another example of doing that. So what about potassium? So potassium is right here on the periodic table. If we were to write the full electron configuration, it would look like this. 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s, and it would be 1 because it's the first one right there, so 4s1. There's the full electron configuration for potassium. If I were to look at the noble gas, that's right before it, so right here, which would be argon. The one right before it, let's write out the electron configuration for that. So it would be 1s2, 2s2, 2p6, 3s2, 3p6. And so again, we see that these two parts right here are the exact same. So for potassium, for the noble gas configuration, we would put in brackets, we would put argon, and then 4s1, just like that. So when you have to write a noble gas configuration, what you're going to do is you're going to go to the previous noble gas, and then you pick up the electron configuration from there. So let's say we were going to do, we'll say this element right here. I can't think of what this element is off the top of my head, but let's say we're going to write an electron configuration for it. What we would do is we would follow this back until we get to right here, until we get to the previous noble gas, the noble gas that comes before it. So we're going to follow this back, and the previous noble gas would be right here, which would be krypton. So what I would do is I would write krypton in brackets like that, and then I would pick up my electron configuration from there. So after krypton would be 5s2, and then I would come down here, and it would be 4d1, 2. and there'd be my noble gas configuration for whatever that element is right there. Okay? Let's try one that's from the lanthanides and actinides down here, just as an example. Let's try, the one from your notes is praseodymium, I think, so PR, which is right here, I believe, on the periodic table, if I remember correctly. Let's write the noble gas configuration for that. So remember that this we think of as being right here in the periodic table. So if I'm going to follow this back, I got to picture that this whole section is really right here. So I'm following this back. I would follow it back here, and it would go up to xenon would be the next one here. So my noble gas configuration would have xenon in brackets, and then picking it up from there would be 6s2, and then going here 4f1, 2, 3. So 4f3, and there's my noble gas configuration for praseodymium. Now keep in mind, by the way, so notice that for the D block, it starts at the third energy level. Remember we talked about at the beginning that the D sublevel doesn't show up until we get to the third energy level. So when you're counting this out, notice right here you're at the fourth energy level, but then once you enter those transition metals, you actually go back down to the 3D sublevel. So be careful with that. Same thing right here. You're coming out of the 6s sublevel, and when you get to the F block, you're dropping to the 4F sublevels. So be careful when you're going in and out of the transition metals for these. Last thing, let's come back over here, and the last thing we're going to talk about is valence electrons. The valence electrons are the ones that are in the last or the outer energy level, the highest energy level. Those are called valence electrons. The valence electrons are important because those are the ones that are actually involved in the chemistry and in all the bonding that happens. All the other electrons are considered inner or core electrons. The way we identify valence electrons, again, we're just looking at which electrons are in the last or the outer shell. So if we look at these electron configurations here for this first one, the one we just did, praseodymium, we've got xenon in brackets, then 6s2, 4f3. So remember, it's the last energy level, so that would basically just be the highest number that I've got in my electron configuration. So if I look, 6 is the highest it goes to, and so if I look, I've got 2 electrons in that sublevel, so the number of valence electrons that this element has is 2 valence electrons. If I look at silicons, this is the full electron configuration. So what I'm going to do is go to what's the highest energy level. And so if I look, 3 is the highest energy level it goes to. I got to account for both of these now, okay? And so I would add these two together. I've got 2 electrons in the P sublevel and 2 electrons in the S sublevel. So a total of 4 valence electrons. And then iodine, this is the noble gas configuration for iodine, but again, same thing. 5 is the highest it goes to, so that would be the valence shell is the 5th energy level, and I would have to add up all of the electrons that are at the 5th energy level, so 5, 6, 7. There'd be 7 valence electrons in the very last energy level for iodine. And that is all we're going to cover in this video.